Okay, hello. Here we are, limits lesson 2. We just defined a limit in our previous lesson. We talked about what it is. It is a theoretical output based on x approaching some theoretical input. Sometimes it exists in reality, sometimes it approaches it but never quite reaches it, and sometimes there is no limit at all. If I evaluate a limit moving from the left to the right, I might have a limit. If I evaluate it moving from the right to the left, I may have yet another limit. They may or may not match. If they match, there is one single unified limit. If they don't, there is no limit. If my limit, when I evaluate my limit, if I go to infinity, infinity is not a limit because it's not a dot on a number line, so there is no limit if I approach infinity as well. Okay. So, without any further ado, let's quickly look at a scenario. It's a quick scenario. Here is a piecewise function that we played with last year, and we saw that, hey, this was like a piece of a curve, then it was a straight line, then it was a hole, then there was a downward line, and we had a f of x equals x squared minus 6. That was this piece, right? So that was creating x squared. How many curves? 2 minus 1 is 1. Positive or negative? Positive, so the curve's pointing up. What's hk? Well, nothing's with x, so 0. K is negative, so 0 and negative 6. So this is a parabola whose vertex would have touched at 0 and negative 6, right? But we only have this much of it because our domain said stop at x is less than or equal to negative 1. So when I got to negative 1, I stopped. I never got to 0 to put that vertex in. But it would have continued. So this piecewise function, if you can analyze your functions the way we did with our 4 questions, you'll be great. So here, that's just an output, right? Here, that's a negative, right? So that's pretty straightforward. Those are easy. Y equals x, that's a 45-degree line, right? Y equals mx plus b. 1x is up 1 over 1, up 1 over 1. Well, y equals negative x is a downward 45. Okay, here it says at 1, x equals 2. But look, 2's down there. Okay? So what's happening here is I'm moving, stop, going, stop, jump, back, down. What's the limit? Ooh, it depends on what I'm approaching and from where. So if I'm approaching 2, my limit is up here, not down there, right? If I'm approaching 0, my limit's there. So that's what we're looking at. That's our refresher. All right. So let's take a look at what's called the limit laws. And the limits are functions, and we can have these limits laws from observations that you can make in the classroom through exploring with the limits that I don't have time to explore on the video. But there are assignments that I will give you to help you to explore and uncover this for yourself. Don't just trust Dr. Taylor, because I can clearly be wrong. All right, so this is saying I'm doing the limit as x approaches 2, but I'm not doing it of just one function, am I? I'm doing it of 2 functions, and those 2 functions are being added together. So what this means is if I say the limit of function f plus g, if I added them together, okay, like if f was x plus 1 and g was x plus 2, together they'd be 2x plus 3. I could put them together first and then plug in 2 and see what the answer was. But what the laws of limit says is sometimes I might want to break them apart. Well, plus is plus. It's kind of like distribution and how it looks, but you don't want to think about it as distribution, okay? But I'm just trying to give you that hook. Notice that I can take the limit of that one and the limit of that one. Can you see that sort of connected look? All right. So what does it mean? It means the sum of a limit equals the limit of a sum. That's basically, in English, what that means. That's the first law. So the first law of limits is the sum of a limit is equal to the limit of a sum. I could write it either way. Okay? And when I do that, evaluating it, I can get whatever I get. Right? So these numbers, I mean, they're just arbitrary. They were from our discussion. Okay? But the point is, if I got 2 plus 0, right? If I put them together, then I end up with getting a 2 as well. They don't, these things down here, they were just part of a discussion that really doesn't apply right now. So let's look at one. Let's make sure that this is true. And in fact, we're going to look at more than one by doing this, Because I'm going to go ahead and tell you, if you could have a limits law for sums, what else do you think, I'm going to ask you first, what else do you think you could have a limits law for? If you could have one for sums, what else could you have? And if you answered differences or subtraction, you'd be correct. And if you think of the four basic fundamental operations in mathematics, addition, subtraction, which go together inversely, multiplication and division, which go together inversely, I have those laws. And those laws will all apply. Those laws are the sum of a limit is equal to the limit of the sums. The difference of limits is equal to the limits of a difference. The product of limits is equal to the limits of a product. And the quotient of limits is equal to the limits of quotients. So the statement's basically the same. You put the different operator in, but the outcome is the same. So we're going to do a multiplicity of them right here. There's a sum, and there's a difference, and there's a sum. So we're going to look at sums and differences together. And so again, if I think about it like distribution, even though it's technically not, but what I'm saying is I can take the limit of each term independently. That's what I'm really saying. I can take the limit of term 1, and the limit of term 2, and the limit of term 3, and the limit of term 4. And when I do that, I get something I can evaluate. I could evaluate it separately, or I could evaluate it together. But there's no way I can combine those anymore, right? It wasn't like the example I gave you where the x's added to x's and the constants added to constants. These terms are all as simplified as they can be in that expression. So let's look at them independently. The limit as I approach negative 2, well, negative 2 to the 4th power, right? I go negative times negative times negative times negative. Those negatives all cancel out, right? Every even power will always give me a positive output. And every odd power will depend on whether my input was negative or positive. So basically it's 2 times 2 times 2 times 2, which is 2, 4, 8, 16. 3 times 16, 48. So I know the limit of that is 48. Also, doing it here, 2 squared is 4. Negative 2 squared is also 4. 4 times 2 is 8. So the limit of that term is 8. Negative 2 is itself, but what's the opposite? So I'm minusing. Minus negative, the opposite of negative. The opposite of negative is positive 2. And the limit of this is 1. Well, the limit of a constant is a constant. That's the fundamental limits law. I should have said that first. My bad. The limit of a constant is a constant. Because what do I put in for x if I have 2? It's 2x to the 0, right? So that x to the 0 is always 1. Doesn't matter what I put in for x. If I put in 10, it's 2 times 10 to the 0. That is a 1. So basically that 2 times 1, that understood x to the 0 behind every constant, means no matter what I put in for x, as long as it's not 0 itself, 0 to the 0 is not going to, then that limit of the constant is itself. So what I end up with is 48 and 8 and 3 and 1, and they go together to become 59. It has a limit. And that will be a solid dot. Why? Because there's no square roots, so I can have a positive or negative input, and there's no fraction, so if I use 0, it doesn't matter. Right? It's still going to work. So that's a discrete limit that I could actually pinpoint, and it would actualize in the graph. It wouldn't be a hole or an asymptote. It would be an actual point with an output there, but it's also a limit. A limit is what it approaches as that input is approached. That's all a limit is. Now here's a quotient. Okay? So with quotients, when I do limits, I always want to see, can I simplify that fraction? Really? We say the word reduce, but simplify is a better word. Because when we reduce a fraction, it's still worth the same value. So I'm not really reducing its value. Reduction is what we say when we say, 10/5 becomes 2. And that's reduced. But it's not really reduced, because 10/5 is equivalent to 2. So it's simplified. Simplified is a better term. We're going to use more technical terms in more appropriate ways, because we're at a high level position now. This is kind of equivalent to college, right? So we're preparing ourselves for college, but we're supposed to be performing at a collegiate level. So I'm going to simplify fractions. I'm not going to reduce them. So the question is, can I just cancel x's out? No, I cannot, right? Let's let x be 2. 2 minus 2 is 0. 2 squared is 4. Plus 2 is 6, minus 6 is 0. So that's 0 over 0. If I cancel that out and I let x be 2, 2 minus 6 is negative 4. Negative 4 over 2 is negative 2 is positive 2. So clearly, I can't just cancel that out, because when I reevaluate it with the same value after I canceled, supposedly giving me the next equivalency, I didn't get an equivalency. I didn't get the same output. So it's not equivalent. So don't, division undoes what? Multiplication. It does not undo addition. It does not undo subtraction. So I therefore cannot just cancel across division to undo some addition or subtraction value in a linked set of terms that are linked together with pluses or minuses. It's very important. Common mistake, don't make it. So what I'm going to have to do is factor this out. Okay? So notice when I put the 2 in, I got 0 over 0, and that was undefined, right? But when I factored this into 2 times 3, right, gives me a 6. Signs need to be opposite. 3 minus 2, opposite signs, gives me a positive 1. So I want a 3 and a negative 2. Now, that's the mental method. It's a great method. It's what you want to strive for, but if you still struggle with it, go back to the table, right? List all your possibilities. 6 times 1, 3 times 2, that's all there are. List them twice, plus or minus, and look at the numbers. 1's to what I want. I want 1x. It's positive, so as is, positive 3, negative 2, bang. Okay? So, now when I do this, what is any number over itself? That's not a 0. It's 1, right? So what this really is a giant 1. That's what that is. It's just a giant, ugly 1. And 1 times this is that, right? So really I'm saying now, what is the limit of x plus 3? That's what I'm saying now. Because 1 times x plus 3 is x plus 3. That's what reduction is. That's what simplification is. It's just taking care of things that appear in the top and bottom that are in a factors. Those are factors get multiplied, and that's why I can undo it with division. These are now multiplication processes, and division does undo multiplication, and that's why I can undo that. Okay? So when I put in 2 now, what's 2 plus 3? Quick, quick, quick. I know it's hard. You got it. It's 5. So while we thought the limit did not exist, or we'd have to do a table, because we were savvy, even though it's artificial, the book problems are artificial. You artificially were able to factor it and get that value to avoid the table. If you weren't doing it in an artificial environment, your computer would be calculating it for you. So you'd have the computer run the table, right? But we're learning how things work and how to do the table, so later when we're doing applications, we know why things are work the way they do, which lets us know what to do for what kind of problem. So it's not, why don't I just learn how to do it in a computer? Because you have no insight when the computer spits an answer at you. You need that insight so that you can put math onto problems. All right. Next, here's one. The limit of this to the 4th minus 1. Well, boy, when I put in 0 here and 0 there, I'm in a bad shape. So I can't do it. I could go to a table right now, but I'm going to think about my algebra. Look, if I could get an h out here as a product in front, I could cancel that. It's gone. I could plug in my 0 and get my answer. Far easier for me. If I can do it, I just don't know if I can. So let's see. Let's do this to the 4th power. I could do it with arrows in a long string and write a big list, but I'm going to do it in columns, like long multiplication algorithm with arithmetic. I'm going to do, well, let's do 2 that's squared, right? So let's do this times itself. Couldn't I write this as 1 plus h squared times 1 plus h squared? Absolutely. And I could write that as 1 plus h times 1 plus h times 1 plus h. That's what I'm doing. So I'm doing the 1 plus h times 1 plus h, and I do h times h squared, h times 1, h, 1 times h, another h, 1 times 1, 1. And I notice the 2 middle terms, as they always do when you do 2 binomials, right? The middle terms can come together as long as I have that common h in each binomial. When they come together, I get that. Okay? That thing there is this squared. That squared times that squared is that to the 4th, right? So I'm going to do this times that. Now it's squared times squared, which is a 4th. Now I'm going to get a 4th answer, and that's how I do my arithmetic method. It's quick and easy. It takes a little practice, but once you've got it, you've got it. Okay? And it's not that bad. It's not like the end of the world if you got to write a little bit. I know that's horrible for some of you, but it really isn't. Write it, think about it, say it when you do it, talk about it with your peers. That's the only way it's going to sink in. Explain it, have someone else explain what you explained, and have someone raise their hands and questions if they don't get it right. And question your peers, and your peer answers the question. Don't get mad at each other and don't be disrespectful. Talk to each other. Explain, and explain the explained thing to someone else, to a third party. That way you can explain yourself, you can hear the ideas of others, and you can explain the ideas of others to a third party. Now you're employable. I don't care what other skills you've got. They can teach you everything else you need to know because you have those 3 soft skills. That's the most important thing you're going to learn in this class. And while you're learning that, you're going to get some calc too. Okay? All right. So let's do this. Look, 1 times 1, 1 times 2h, 1 times h squared, 2h times 1. I put them under the like terms, right? 2h's. So it's kind of like putting a 0, but you're really not putting a 0 in that place. You're lining up like terms. And that's what you're doing when you put the 0 on arithmetic. You're lining up tenths with tenths and hundredths with hundredths, right? You don't want to put tenths under ones. It's the same thing. But now you're thinking about it and what you're really doing. So you've always been thinking algebraically. You just weren't told it when you were taught those algorithms. And that's why algebra seems hard when you get to high school. It's the math is taught poorly in elementary and middle. So 2h times 1, 2h times 2h is 4h squared. Put it under the h squareds, right? 2h times h squared is 2h to the cube. There's no, so I put it out in front. Then again, h squared times that under h squared times that under h cubed, h squared times that is h to the 4th. When I add all the like terms down in the column, I get my final answer. H to the 4th plus 4h cubed plus 4h plus 6h squared plus 4h plus 1. Okay? So now, look at when I put that back in. So in red is me putting in for this what that's worth. When I put that in, I had a plus 1 on the end of it, but I had a minus 1 in my original problem, right? So I have a plus 1 minus 1, which becomes a 0, and now there's no constant on the end. No constant on the end means every term has what in it? An h. And if every term has an h in it, I can factor it out in front. Take an h out of h to the 4th, it becomes h cubed. I'm undistributing. That's what factoring is. Undistributing an h from every term, right? So think of it this way. If I'm factoring an h out, I say h to the 4th divided by h is h to the 3rd. H to the 3rd divided by h is h squared. H squared divided by h. That's what you're doing. Okay? And now the h in front and the h on bottom can cancel, and I'm left now with this simple expression, no fractions, which means I can plug my 0 in now and get my limit. So this is the hard stuff of evaluating limits, where you're using the limits laws, but now we're having more complicated statements to evaluate limits. Sometimes you got to expand and then combine. That's what we just did. And the one before, we factored and then canceled. Sometimes you do both things. It's amazing what might have to be done, but you can always fall back on the table. If you think about it, a t-chart's just a table, and when you didn't know how to graph, you made a table. Well, when you don't know how to do that limit, you make a table, and you do how it approaches it from each side. So this limit, as I plug in 0, well, that's wonderful. 0, 0, 0, 4. So I love working with 0 for that reason. Better than 1 even. Okay? So this limit approaches 4. Have no idea what that shape looks like, but you can type it into Wolfram Alpha and look at it. Okay? All right. Now look at this. Here are our steps. First thing I'm going to do when I'm evaluating a limit is I'm going to plug it in. Okay? When I plug it in, it'll either give me an answer or it'll give me something that's undefined or indeterminate. Okay? So when I do that, and I get a discrete value, I'm done. If I don't get a discrete value, I go to steps 2, 3, 4. Step 2 then, factor. Can I factor? Is there a way I can factor that? If I can, great. And then I factor it with the mind of canceling. Just because some two things factor doesn't mean it's going to be great. They have to factor in such a way that one of their factors cancels out top and bottom. Otherwise, there's really no value in the factoring. But you still need to check. I might expand, which is what I did last time. Okay? Sometimes I expand and combine and things cancel. And once they cancel, they may factor again, and then something else might cancel. You never know, and you keep playing with the math. All else fails, push comes to shove, you throw a table at it. Okay? So, look at this. 9 minus 9, nothing. 3 minus the square root of 9 is 3. 3 minus 3 is nothing. 0 over 0, indeterminate. So this doesn't work. Yeah? So I can't factor and I can't expand. Now I can tell you this, and this might give you a yieldable way, and most people don't see it right off the bat, but if I multiply this by its conjugate pair, right? What I get is basically 3 squared minus t, or 9 minus t. Whew. So, but then that would also, I'd have to do that to the top, so it wouldn't be 1, right? But it would be something where I was able to get rid of that square root at the bottom, and then I could evaluate it and not have to worry about it being imaginary. But whatever, the table works. So I approach 9. At 9, I get, actually I don't get that, do I? I actually get that, right? So at 9, I get an undefined or an indeterminate, right? So at 8.9, I get that, 8.99, so that seems to be approaching what? I'm going to say 0.99999, it seems like it's approaching 6, doesn't it? But maybe not. But this is when I put in 9.1 and 9.001, so what's happening here is, this can't be right. So I'm coming here closer and closer and closer. Oh, this minus 0.001. Okay, good. All right. So less than 6, but closer to 6. This would be yet closer. So they're approaching 6. Therefore, I'm going to say the limit is 6. And remember, these are lessons that are 1 or 2 years old, actually 2 years old. So I'm pulling these lessons up so that they were made and I could give you a quick video presentation. So if I seem like a little like I'm not sure what's coming next, it's because I'm not. All right, but I got to get these done, and I'll make more refined ones maybe, probably, but these have to get done so you can get this class going. All right. So, now the next part of this lesson was Pascal's triangle. And the only reason I want to talk about Pascal's triangle is because it helps me to unfold binomial expansion.